Hey there and welcome. Every network has a weak spot. And for most of them, it's that one single gateway that connects everybody to the outside world. If that thing fails, everything just stops. So today, we're going to fix that. We're going to walk through step by step how to build in some gateway redundancy and create a network that's actually resilient.
So take a look at this. This is our blueprint. On the surface, this looks like a totally solid standard network, right? You've got your core, your distribution, and your access layers. But if you look a little closer, it has a fatal flaw, a single point of failure. If that one main gateway router decides to go down, the whole network is cut off. Let's dig into that weak spot. So let's ask the big question. What actually happens when that main gateway fails? Well, the answer is simple, and it's brutal. A total outage. No internet, no access to other parts of the network, just complete radio silence. And that is the exact problem that we are here to solve today.
And this is our solution. Gateway redundancy. It's not so much a product as it is a design philosophy, and it has one crystal clear goal: to make absolutely sure that the end devices, the PCs, the servers, the things people actually use, never, ever lose their connection to the network, even if a piece of hardware fails.
Now, the specific tool we're going to use to pull this off is called HSRP, or the Hot Standby Router Protocol. It's this really clever piece of Cisco tech that lets us take two separate physical devices and basically trick the network into seeing them as one single, super reliable virtual router.
So how does it work? Honestly, the logic is brilliantly simple. Think of it like an airplane with two co-pilots. You've got one pilot who's active, they're flying the plane, handling all the controls. And then you have the other pilot on standby, just watching everything, totally ready to take over in an instant if anything goes wrong. The most important part is that the passengers, our network users, they don't care who's flying. They just know they're on a plane. That plane is the virtual IP address, and from their perspective, it never, ever goes down.
All right, let's get our hands dirty and start building this thing. We're going to work from the ground up, starting at the foundation. Layer 1, the access layer. This is where all of our users and their computers actually plug into the network. Now, before we just start throwing commands at the screen, let's ask a really important question. Why are we even bothering with VLANs in the first place? Because, understanding the why is what makes you really good at the how.
And the answer really comes down to two things: control and efficiency. VLANs let us digitally chop up a single physical switch into multiple, separate virtual networks. This means we can group users together, say by department, and keep their traffic isolated for security. It also quiets the network down, preventing a big broadcast storm from one group from slowing everybody else down. And here's what that looks like in the real world. We're on our access switch SA, and you can see the commands are super simple. VLAN 22, and then we give it a name. Name users_VLAN 22. We do the exact same thing for VLAN 33. And just like that, boom, we've created two completely distinct, logically separate networks on one piece of hardware.
Okay, so we've got our separate VLANs sitting on one switch. But how do we get their traffic up to the rest of the network so they can actually talk to people? Well, that brings us to our next why question. Why do we need to configure trunks?
Think of it this way. Trunks are the multi-lane highways of our network. A normal access port is like a single-lane road. Only one VLAN can use it. A trunk, on the other hand, is like a freeway that can carry traffic for all of our VLANs at the same time. You can see here, on interfaces E0/1 and E0/2, we use that switch port mode trunk command, and that's what creates the freeway up to our distribution switches, letting both VLAN 22 and 33 get where they need to go. Okay, let's move up a layer to the distribution switches. Now, this is the intelligent core of our whole design. This is the redundant brains of the operation where all that HSRP magic is about to happen.
All right, this is where it gets really good. We're on switch S3, and this is going to be our primary gateway. I want you to notice two key commands. First, standby 22 IP 192.168.22.254. That defines our virtual IP. That's the cockpit address we talked about. Second, look at this, standby 22 priority 110. That higher number is what makes this switch the boss. It automatically wins the HSRP election and becomes the active gateway for all the traffic in VLAN 22.
Now let's hop over to our backup switch, S4. The virtual IP command? It's identical. It has to be. But look at the priority. We've set it to 100.
And since 100 is lower than S3's 110, this switch gracefully loses the election. It knows its job is to just step back, go into the standby state, and wait patiently, ready to jump in if S3 ever disappears.
So let's just put it side by side to make it crystal clear. It all comes down to one little number. S3 has a priority of 110, which crowns it the active king. S4 has a lower priority of 100, which makes it the loyal standby. They're constantly checking in with each other, and if the king ever falters, the standby instantly takes the throne. That right there is seamless failover in a nutshell.
We've done it. We've built a resilient internal network. Now we just need to connect it to the rest of the world. So we're moving up to the core layer, which is going to handle all of our access to the internet.
Okay, so inside our network, we're using all these private IP addresses, but you can't use those on the public internet. So how do all of our hundreds of internal devices get online? This leads us to our final why of the day. Why do we need something called NAT overload?
NAT, or Network Address Translation. It works kind of like a corporate receptionist. It takes all the requests from our hundreds of private internal IPs, and it sends them out to the internet using just one single public IP address. Then, when the replies come back, NAT remembers who asked for what and sends the traffic to the right computer inside. It's the magic trick that lets our entire company share one public internet connection. The configuration is done, the theory is all in place, but in networking we have a saying, you don't trust, you verify. So let's move on to the most satisfying part of any project, proving that our resilient network actually works the way we designed it to.
Okay, moment of truth. We've laid the foundation, we've configured the brains, and we've opened the gateway to the internet. Now it's time to see the results of all our hard work.
Here are the keys to the kingdom. That show standby brief command, that's your new best friend. It tells you instantly which router is active and which one is on standby. Then you have show VLAN brief and show interfaces trunk to confirm your whole layer 2 foundation is solid. And finally, show IP route just verifies that your network can see a path to the internet. This is your essential verification toolkit.
So, what did we actually accomplish here? Well, we built a high availability network. Remember that problem we started with? A single failure meant a total outage. Now, a device can completely fail and the network just heals itself, automatically. No frantic calls to the help desk, no one has to manually change anything. We've delivered on the ultimate promise, a network that is, for all intents and purposes, always on.
And that brings us to the end. We successfully hunted down and eliminated a major single point of failure. And that kind of leads to the final thought I want to leave you with. Now that you've solved this one, what's the next weakest link in your own network? Because building a truly resilient system, well, it's a continuous journey. Thanks for joining me.